Okay, let's get started. So last time I made a lot of mistake. I need to make correction, and then I need to give a more supportive evidence and example for Raychaudhuri equation and so on. So let's review that. So last time I introduced the notion B mu nu delta nu C mu. Where we assume this is C mu is something like the time vectors, or some proper time like this way. Okay, so it's just so to consider geodesic congruence or whatever time like geodesic congruence like this way. And we just consider the tangent vector along this time like geodesics, like this way. And then we consider the following things. So the theta is the B mu nu. So this is time like, so I'm just consider time like H mu nu, and then sigma mu nu is B mu nu minus 1/3 H mu nu theta, and then omega mu nu equal B antisymmetric, like this way. And then so this is called shear, and this is rotation, and this is the contraction, and so on. And then so Raychaudhuri equation is the how this theta and sigma omega will change along this geodesic congruence. So that's the case. And then to give the meaning of another meaning, so to introduce, so I call it so-called extended curvature. So let's call this is sigma. And then one can introduce, so H mu nu is the induced metric in here. Okay. Induced metric only here. This is induced metric. Okay. Likewise, one can define the so-called extrinsic curvature. So extrinsic curvature is just so extrinsic curvature is the same as the B mu nu along the hypersurface sigma is something like a K mu nu is the down mu, the C mu is B nu mu, and this is called extrinsic curvature. Okay, and it's a purely spatial. And another way to define is K mu nu is the Lie derivative of this metric. How the metric would change along this geodesics. That's the induced metric. And so that's the another way to define that. And here, where C, sorry, so here when C, so the difference, so here we assume that C is orthonormal. And orthonormal to sigma. That's the, so that's how it works. And this can be understood as sorry. So this is 1/2. This is 1/2. So 1/2. It's just time derivative along the geodesics H mu nu. So this H mu nu induced metric with respect to time like this. Okay. So that's how the extended curvature is defined. Is tau T. And then if you take the trace, so if you take trace of this one, is I call it K, which is H mu nu, is K mu nu. So when you take a trace, you just take a trace with respect to induced metric H mu nu. And this is equal to, I call it theta. It's in fact equal to theta. So the theta is the trace of the extreme curvature on the hypersurface, spatial hypersurface. So that's the another way to look at the theta. Okay, and then so that's the how you define how you can see the theta in the yes. Somehow, sorry. So my notice has a lot of typos, still lots of typo. Sorry about it. Yeah. So I will correct it. So for instance, I haven't finished the writing of this singularity theorem yet. I will explain more in detail, account than the lecture notes. So I think today it's better to focus on black hole. Okay. So that's how it works. Okay, so so Raychaudhuri equation, or the important part is like this way: rho the rho theta is equal to -1/3 theta squared minus sigma mu nu minus omega mu nu minus r mu nu c nu. Okay, so that's the case. And as you can easily see from here, so omega can be set to be 0. So as an initial condition, you can set that the omega rotation of the hypersurface is 0. So then as we see last time, omega equation omega rho, the rho omega is a function of omega. I'm not going to write down everything. Maybe I should. Yeah. Minus 2/3 theta omega mu nu plus the 2 times omega and sigma. So indices I'm not going to write. So if the initial condition omega is 0, so its left hand side is always 0. So therefore, along the time-like geodesic congruence, the omega stays 0. Okay. So it never not rotate. So the curvature never rotate. Okay. And the shear, but on the other hand, so the shear is just the distortion of the circle like this way by keeping area. This will occur due to the space-time curvature. Okay, so from here, as you can easily see, so right-hand side. So if you assume this is the entire thing is negative, if you assume so this is some energy condition, the right-hand side is always negative. Okay. Right-hand side is always negative. So as you go along the geodesic, always theta is essentially the area. So the theta is become negative, contraction or expansion, depending on sign. Theta is kind of like they can be understood as the area of this circle. So therefore, it's always, even if you start with sigma, and the initial condition is like something like expanding, but always something like how to say? Eventually, it's contracting eventually because of right hand side. Okay, so that's the what the Raychaudhuri equation mentioned. Depending on time. Anyway, okay. So example is the expanding universe. So if you consider ds square is equal to minus dt square plus a of t square, dx square plus dy square plus dz square, like this way. So if you consider like this way, and you can easily see that the is in a space component sigma is essentially the one in given here. And time direction is this one, t. So this is x, y, z direction. So this is spatial circle. Then you can take u alpha is the, or c alpha, maybe c alpha is minus time derivative. If alpha, then the b alpha beta is del beta c alpha, and this can be computed like a dot over a h alpha beta. So h alpha beta is the induced metric on the sigma, so which is this guy. Okay. So one can easily compute this one. So therefore, theta here is just take a trace of this guy. So therefore, this theta is 3 times a dot over a, and which is the a cube over 1 d dt a cube. Okay. So this is kind of like intuitive, makes sense. The volume of this hypersurface is proportional to a cube. Okay. And if you take a derivative of this one, you get theta. Okay. So this is the consistency what we have found here. So essentially taking the h mu nu derivative is essentially just taking derivative of a volume of the spatial surface. Okay, so that's the time derivative. And last time, so Ray-Chandler equation is something like over there. So this is time like. And then for no geodesic congruence, this will change to, this term will change to 1 over 2. Okay? So this will change to 2 for no geodesic congruence. And of course, you have to change here appropriately you have to change appropriately. I forgot how you change the. So here it just new like the vector. It just the reason is that so I think you should have asked. I think last time it was raining, so not so many students are here. So, but you should have asked why 3 to 2 will change. This 3 is actually the direction d minus 1 is equal to 3. D is the space-time direction. Because I mean, if you take the time-like geodesics, orthogonal component has a 3 direction. That's why you have a 3 here. Okay, 3 here. On the other hand, in the case of no, so if you have a no geodesic congruence, whatever, no geodesic congruence like this way, and I call it this one is k. That this is k mu. And k mu. And then k mu is satisfied whatever. So it's affinely parameterized. K mu is equal to 0. So k is something like delta lambda. Is a lambda is just a affine parameter of the no geodesics. So since it's a no, so k squared is equal to 0. Okay, so it's k is the tangent to this geodesic, also orthogonal to geodesic, because of k squared equal to 0. So there are no independent, no d minus 1 independent vector orthogonal to k mu. Okay. So yeah, there are no independent d minus 1 independent vector orthogonal to K mu, excluding except so excluding K mu itself. Because I mean K mu itself is also orthogonal to this K itself because K squared is equal to 0. It's a norm. Okay. But here there are no d minus 1 orthogonal vector. So therefore one has to define the following vector. So K mu dot L mu is equal to minus 1 and L squared is equal to 0. We have to find such a vector. So it's a null itself. L is a null, but the contraction with K will give you minus 1. So suppose K is equal to something like locally 1, say 1, 0, 0. So this is the okay. But then L can be something like L can be like something like this one. Okay. Which is a minus 1, 1, 0, 0. Like this way. Okay. You can take this one. Then it's a null itself, and then but if you contract with K, you get a minus 1. You have to appropriately normalize. In this case, minus 2. So therefore, you have to normalize, say, square root 2, maybe something like that. Because I mean, if you have a 1 to minus 1, it's just normalization. So then you just do the parallel transport along this null geodesic congruence on L mu. So you can have a vector field, like this kind of vector field, L mu. Okay. So then, so you can have the something also orthogonal to this. This is hypersurface. It's not hypersurface. It's a d minus 2. How to say? Submanifold or submanifold? Okay, submanifold. Okay. Space-time submanifold, such that the induced metric is something like a G mu nu plus K mu L mu plus L mu K mu. Okay. So this is how you define. So it's on d minus 2 submanifold which is orthogonal to both L and K. Okay.
Here K is null vector, right?
Null vector,
L
yes.
is also
Null vector, yes.
How their dot product is minus equal to 1?
Okay, but you just take the contraction with 1, 1, 0, 0. So the one you agree 1, 1, 0, 0 is the null, right? Locally. So if you consider Minkowski metric locally, 1, 1, 0, 0 is the null, right? Minus 1, 1, 0, 0 is also null, right? But if you take a contraction, you get the minus 1, right? If you appropriately normalize. Okay. So then you can define the sum d minus 2 submanifold which is orthogonal to both L and K. This is very similar to what you learned in electrodynamics. So in the polarization of the electromagnetism, only 2, right? In 2. So orthogonal polarization of the electromagnetic field is just only 2 polarization, right? On the other hand, for time-like or massive particle, you can define as 3 orthogonal direction. But on the other hand, for null geodesic or like a massless particle, the polarization or orthogonal to this vector is only like a d minus 2 or 2 in d equal to 4. It's just only 2 dimensional. So that's how you define. Okay. And, how you define this projection? So this is the induced metric on this in this surface, or maybe surface is okay, or whatever you call it. It's not hypersurface. It's not codimension 1. It's codimension 2. Codimension 2 surface, and then you can define the B mu nu for, so this is a null case. This is a null case. And then you can define the null case is something like a B hat. I call it B hat for null. Is H rho mu, sigma rho mu down sigma H rho. Okay. And this is 1/2 theta H mu nu plus hat mu nu plus omega mu nu. Okay. So this is the symmetric part, anti-symmetric part, symmetric part, and this is trace part. Okay. So this is trace part. And then we define the Raychaudhuri equation. So you can compute the Raychaudhuri equation by changing a property. 3 to 2 is because of the dimension of orthogonal surface is different from time and then no coordinate. Okay? And then you have to change appropriately from the time-like geodesic or to no geodesic. So that's how you change the Raychaudhuri equation and so on. Okay, so this is what I have missed have failed to explain last time. Okay, so and then we talk about the focusing theorem last time. Okay, so as I mentioned right here, so if you assume so you just assume some appropriate energy condition such that the entire thing is negative. So the upper one is called strong energy condition, and the lower one is called new energy condition, and so on. Then the equation can be written is a d theta of d tau in its time-like case is the plus 1/3 theta square over third is less than 0. Okay, so you just bring this one into the left hand side, and the right hand side is equal to 0. Once you assume the sorry, I think this should be plus. Yeah, sorry. Once you assume the rotation is 0, so this is 0 negative, and this is negative. So therefore, this quantity is negative. Okay. So, yeah. So therefore, there's a sigma, and suppose the initial condition, the theta tau is equal to 0. So this is tau equal to 0. This theta 0 is negative. Okay. Then one can just show that this is theta 0 inverse plus tau over 3. Therefore, something like how to say? There is a caustic point will appear. Point appear when this how to say proper time is the less than 3 theta 0 inverse. Okay. So if it is a negative quantity, if this is a negative quantity, at some point when tau grows, right hand side become positive, which means the theta become positive, right? So because of this intermediate value theorem, so first theta 0 is the okay, how should I write them? This is theta, and this is tau, and tau equal to 0 it's negative, theta 0. And at some point it becomes positive, right? It should be positive. So therefore, at some point theta has to be 0. theta inverse has to be 0. So, sorry, this is simple. Okay, theta inverse to be 0. Okay. So therefore, theta inverse to be 0 means theta goes to infinity. Okay. Theta goes to infinity means that this is really shrinks to the point. Shrinks to the point. Okay. So theta diverges. Infinity means they contract to the point. Okay. That's the that's the case. So therefore, so this theta is essentially, area inverse, and the area inverse goes to 0 means that there is some focal point will appear. This point is called this point is caustic point or focal point. Sometimes it's called conjugate. Walt mentioned conjugate to sigma. Something like this. So this is called Fulkerson theorem. Okay. So when theta diverging means that really like this area goes to the point. So you cannot measure the area.
Light does not mean like this going to the infinity rather than going to the point. Theta means expansion or contraction, right?
That's true, but here as you can see from here, so a goes to infinity means a goes to infinity, it becomes 0, right? Theta goes to 0 in the expanding universe. That is, but when a goes to 0, it's really universe is contract to the point, right? So therefore, theta goes to diverging. So for this from this expanding universe, you can easily see that the theta goes to infinity is the really contraction, whereas the theta goes to 0 is the a goes to infinity. Okay, so that's the case. And for new case, it's everything. So that this 3 really coming from this orthogonal dimension. So you have to change this one to 2. Okay, and this one's to 2, and this one is to 2, and then this is no case. And the same theorem will hold. So that's last time I failed to explain. So I hope you guys understand at this moment. Okay, any question at this moment? Anyway, so yeah, if you have a question, just tell me. Then for instance, for this kind of change, I should have explained last time. So if you think it's unclear, just ask me during the lecture. Okay. And then it's causal structure of the spacetime. Causal structure of spacetime. And the causal structure of spacetime, I also taught a lot of lie last time. Causal structure. So it's just a name. So definition. So causal curve. Causal curve is the time-like or the no curve. No curve. Okay. And then causal feature J plus minus of P is the Q in spacetime. So the M G mu nu. So this is the space-time. Then Q in space-time and Q and P are connected by causal curve. And depends on plus minus. Plus is future, future directed, and past directed is minus. Plus corresponds to the future, minus corresponds to the in the past. Okay, so that's the case. And then, yeah. So if point, so let's see, the curve. I think I forgot to. So the curve gamma is called extendable. Extendable. I mean, I searched last time. Extendable, extendable. I don't know which one is correct name. Somehow there are lots. Both are used actually. Extendable and extendable. But Witten used the extendable, so I follow it. I don't know. I'm not native English speaker, so I don't know which one is correct. For instance, I look at the word. He used extendable somehow. Anyway, if gamma can be extended from its endpoint. So if you have gamma like this way, and then it stops like this way, and in space-time it still can extend like this way, it's called extendable. Otherwise, gamma is called inextendable. Extendable. By the way, so I think a reference is the section 8 and 9 of Word. And also there is a very nice lecture by Witten. Witten is called, I don't remember the light rays. I don't forgot the light rays singularity, most likely. Singularity and all that. Something like that. So those are the reference for this kind of stuff. It's I don't remember the. Oh, okay. I printed out, so I know the archive number. Okay, archive number is 1901.039 03928. So that one is very good. Okay, and then the okay, and so future d plus minus of u is called yeah. Before going that okay. Anyway, so if you go to this is point P, right? So the j plus minus of u, where u is some subset of M. So this is just a union of P inside a U, j plus minus of P. That's a definition. I will give an example later, so don't worry about at this moment. D plus minus of U is the so the P in M every. So it's important. So this is the important part is every. Okay. Inextendable, extendable. How to say? Causal curve intersect with curves through P intersect U. Okay, that's the definition. So it's called a future or past domain of dependence. Domain of dependence. Okay, so I will give that example. So those definitions, unless you just give an example, you never understand. So then last time I didn't give an example properly, so it's not right way to teach. So maximally, so you guys just feel free to ask me during the lecture. So maximally extended rational stone space-time. So it's something like I forgot how to draw. Let's see. Let me try. Like this, right? Yeah. Okay, good. Still. So this is singularity, and so okay, and singularity, and say sigma is something like let's use a different color. Sigma is something like this one, and sigma is hypersurface, spatial hypersurface like this way. Then J, so let's see. J plus of sigma is something like how to say? So let's look at the all the point Q, such that the Q and the any point in sigma can be connected by causal curve. Okay. So let's look at the example. So this point can be connected by any point in here, like this, whatever time-like curve. So this is the including J plus. On the other hand, this point is the past. So therefore, you cannot connect between future causal curve. So therefore, this is excluded. How about this point? This point can be connected by any point. Not any point. This point in by a time-like curve. So therefore, this point also J plus sigma. Likewise, here is also you can just how to say find some curve like this way. So therefore, in fact, J plus is any part in here. Okay. So this is J plus. Okay, J plus of sigma. Okay. On the other hand, how about the J minus is similar? How about here? Future domain of dependence. Okay. Every inextendable causal curve through the intersect U. Okay. Every. So let's look at this point here. Okay. Every causal curve, point P, intersect with sigma. Every causal curve inextendable one is just is this one, right? Inextendable is this dependence, right? Do you understand what I mean? Every causal curve. Okay. So therefore, every causal curve intersects with sigma. Okay. So this P is inside a D plus of sigma. On the other hand, if you look at the point P here, okay, every causal inextendable one is something like this one, right? Okay. It's included like this region. Okay. Do you understand what I mean? So therefore, this curve is an extendable one. Okay. Does not intersect with sigma. Do you understand what I mean? So this curve is the inextendable causal future like curve. Okay. Okay. Through. Okay. So it's a path directed. It's fine. I mean, path directed curve hits in the singularity, but it's inextendable. But it doesn't intersect sigma. Okay. So therefore, this P is not included this D plus. Okay. So therefore, D plus is in fact the region in so D plus is in fact the region here. Oops. So this is D plus of sigma. Okay. Likewise, yeah, D minus is only this part. D minus is this part. This is D minus of sigma. Okay. And then the rest of part is the rest of the bottom part is the J minus of sigma. J minus of sigma. Everything. Okay. So that's how you define the future domain of dependence. Dependence means that yeah. So this point is somehow influenced by sigma. Influenced by sigma. Okay. So that's why it's called future domain of dependence. But point P here receives some influence from the except the sigma. So from the timeline curve here and timeline curve like this way, will intersect with P. Okay. So therefore, but this timeline curve never intersects sigma. So the information will affect what's physics at the point P. Okay. So therefore, it's not the how to say future domain of dependence of sigma. That's
You mean they are not causally connected?
I mean, it's causally connected. I mean, it's causally connected like this way, causally connected, but not all the causal curve is from sigma, not all. Okay. So therefore, there is some kind of like a extra information you need to determine physics on P, at P. Okay, so that's what you mean. Okay. And then the last time I talked about this, I hope I remember this notion, right? Is it achronal notion of achronal such that the sigma is the hypersurface sigma or U, whatever you call it, U, such that any point P and Q on U are not connected by how to say timeline curve. Cool. And a counterexample, this is a counterexample last time. So if you consider the S1 cross R, and then if you consider sigma is something like this way, then so I call it this is hypersurface sigma, then the P and the Q are connected by timeline curve. So therefore, this is not the achronal. Okay. achronal. And then I introduce so-called okay, and then Cauchy surface, and then I will say global hyperbolicity, hyperbolic. So if it is there exists a sigma hypersurface, space-like hypersurface, it's space-like, right? Anyway, hypersurface, okay. Hypersurface such that d plus of sigma and d minus of sigma is equal to entire space-time. This is called sigma is called the Cauchy surface, and M is called global hyperbolic. Okay. So example. So therefore this is not. So sorry, this is not. So last time I told you complete wrong thing. Not a globally hyperbolic. Globally hyperbolic. Because I mean these points are, there's no way to write down the entire space-time by d plus and d minus. Okay, there's no way. So this is not, and the sigma is not the Cauchy surface. Okay. It's a partial Cauchy surface. Is it called partial Cauchy surface? No. Intersect any person at the most ones is called. No, it's not Cauchy surface. So it's not. It's okay. Partial Cauchy surface. Okay, maybe I should give you a definition of partial Cauchy surface. Okay, partial Cauchy surface. Okay, definition of partial Cauchy surface. Cauchy surface. Sigma is at the hypersurface. So this is definition. Hypersurface sigma such that any causal curve intersect with sigma at the most. This is important once. At most one. Okay, at most once. So therefore, I already rest. This is not partial Cauchy surface. Achronal one, not achronal one. This is clearly not the partial even Cauchy surface, because as I mentioned, it intersects with twice, right? Causal curve intersects with twice here. So this is not even partial Cauchy surface. On the other hand, this sigma is a partial Cauchy surface. Okay, it's a partial one. Because this curve do not intersect with sigma, but it's okay because the at most ones means 0 or 1. Okay, at most means so this timeline curve does not intersect, but this timeline curve will intersect with ones. Okay, so therefore it's a partial Cauchy surface. But however, it's entire space-time cannot decompose d plus and d minus of sigma, so therefore it's not the Cauchy surface, and the space-time is not global hyperbolic.
Is there any way to cross twice in this example?
I mean, of course you can. So this is important for the proof of the proof of the singularity, Penrose singularity theorem. Okay, so let's give you the example of the. Okay, let me give you an answer in this way. Okay. So maximal extended, how to say, Schwarzschild spacetime. This is the global hyperbolic. And the sigma is something like this one. This is a Cauchy surface. And the answer to your question is that there is a hypersurface that intersects with something like that. So if you consider a hypersurface like this, sigma prime, then time-like curve like this way will intersect twice. So therefore, this is not partial Cauchy surface. The sigma prime is not the partial Cauchy surface. Okay. But it's hypersurface. It's a hypersurface. It's a codimension 1. So it's still like a hypersurface, but not the partial Cauchy surface. Okay. So this is a counterexample of partial Cauchy surface inside a global hyperbolic spacetime. Okay. Any question? So as you know, so this part is the d minus of sigma, and the upper part is the d plus of sigma, and the d plus and d minus will, how to say, exhaust the entire space-time. So therefore, this is a global hyperbolic. Okay. Okay. So any question at this moment? Okay, and then the important thing, example, Euclidean example of a caustic point. Okay. Consider sphere S2. Okay. S2. What is the geodesic of this S2? This great circle, or any great circle, you start with a point P. Point P here. And consider the all geodesic from P. Okay, geodesic is something like this one. Okay. Another geodesic. This way, like this way. So any geodesic from P will, there's a focal point, say that the northern hemisphere starts with P, and the cosine point is the southern hemisphere Q. Okay, so any geodesic from P will just, there's a focal point at the Q. Okay. So this is one example, Euclidean example of focal point, okay, or caustic point. So anyway, so whatever you write is okay. So therefore, the Q can be understood as a focal point of the, for instance, sigma can take, whatever sigma can take, I need a color choke. So sigma can take like this way, and consider the orthogonal the geodesic coming from sigma and just a focal point at Q. Okay. So that's one Euclidean example of focal point. And this example is very important in the following way. So in Euclidean case, geodesic is the geodesic is locally minimal. How to say? Locally a curve with locally minimal length. Okay. So for instance, if you look at this sphere case, anyway, bear with me. My drawings getting worse and worse. Anyway, if you look at this sphere case, if you look at the point P and Q, like here. I mean, okay, let's do the following example. So if you consider P here, and whatever P here, and Q here, so the gray circle which connects P and Q is a geodesics. And you just do the continue this example. So at this point is okay. When Q is just moving around here and here is okay. But the important thing is once you are cross Q. Okay, once you cross Q, okay, this geodesic is no longer and Q is here. Once you Q cross the south pole, this path is no longer minimal length. Okay, no longer minimal. It's a geodesic, but not the minimal length, because the opposite is the minimal one. Okay, opposite one. So the important thing is that this cosec point. Once you have a cosec point, the important thing is why the way to define find why this point is no longer the how to say minimal length is that if it is a cosec point, one can slightly how to say shift this geodesic to the slightly like this way. Okay, you can shift like this way. Okay, but still this is geodesic. It's a gray circle. You can have like this way. Am I writing correctly? Yeah, I think like this. Okay. So you can still do, and it just meet with focal point, right? Focal point. And you just consider the P and the Q connect by blue line, and connect with Q. So this is, let's go S because southern pole, and this is northern pole. So blue and the, let's go, okay, maybe yellow. Yeah, I can write that yellow. Okay. Okay, no, not yellow, red. So originally red one. So we consider red one. Originally consider red one. Okay. But this red one, north to south part, is the same as blue part of north to south part, right? Okay. So you can consider the blue part plus so blue north to south, and then south to Q. It's the same as, okay, maybe I just write down like this way. Kink. Maybe something like north to south and then Q. Okay, it's the same as north to south, south and Q. The length is the same. Okay. However, so it is this blue plus this what's that? Red one has a kink, right, at the point at the south pole. It's no longer smooth at the point at the south pole. So therefore, there is a shorter parcel like this way. Okay. So you can just there's a kink. Since there's a kink, you can just slightly smooth out. You can smooth out like this way. It's a shorter parse. Okay. And if you consider try to shorter parse, and this yellow part is just go to opposite this dotted line of yellow, that is the shortest one. Okay. So that's a way to prove intuitively why this red line is not the maximal, the minimal length. Because there is a caustic point. At the caustic point, you can just perturb this geodesic to geodesic by just shifting. It's called Jacobi field, but I'm not going to explain what's the meaning of Jacobi field. Red to blue. When you shift the red to blue, there's a kink will appear at the caustic point. Okay. And then from there, you can smooth out the curve, which is has a less length, smaller length. Therefore, this is the important part when you prove this singularity theorem. Okay.
Why have you used Berkeley?
Huh?
Berkeley.
Dimension. So north to Q. This red one is geodesic. It's geodesic, but not the minimal length, right? From N to Q is a geodesic, but not the minimal length.
Not minimal.
Yeah.
Locally as well.
Locally, if you look at locally, this is a minimal length, right? So those are minimal lengths. But if you look at it globally, it's not minimal length. That's what I mean. So this is the important part of the theorem of this Penrose and Hawking. How to prove this one. The same thing happened in the Minkowski. Minkowski space, if you look at time-like curve, time-like geodesic, it's a maximal length. Okay? So Minkowski, okay? In Minkowski case, so time-like geodesic, or a caustic geodesic, has the locally a maximal length. Okay. So you just consider point P and consider whatever time-like geodesic Q. This is a maximal length. One can just consider you can just consider that this how to say like this. So this yellow line is some like a new curve. New curve length is always 0, right? So therefore, if you just look at how to approximate this time-like geodesic by new curve, this is length is 0. Yellow one is length 0, whereas this the white one has some length depending on the sign, whatever. G mu nu, dx nu, square root minus if you do this integration. So this will give you positive length, and this is a maximal in Minkowski time, space-time. And situation will change once you encounter caustic point. So important. Important theorem is that the consider global hyperbolic with the space-time M with the quasi surface sigma, then any point P to sigma that has the with maximum length cannot contain any point on P. Okay, co-circle from does not have caustic point. So this is a theorem. Okay. So let's prove that this one by. Let's prove by contradiction. Suppose sigma, there is sigma and point P. Okay. Something like what was that? And there's let's consider the following things. So there's some time-like curve. So this is the maximum length. Let's consider maximum length. From P to sigma. Okay, P to sigma. Maximum length means that in the Minkowski time, it's the shortest path. Okay. I mean here, in minimum length, this is, if you just approximate a null, it becomes the length 0. Okay. But that is not the, how to say, like in the Minkowski sense, it's not shortest path. Okay. This geodesic should be, how to say, shortest or maximum path. Okay. But suppose if you have focal point in middle, Q. Okay, focal point. So then you can just approximate to the geodesic like this way. Okay. So this geodesics, as again, from red to blue, it's like a red to blue. You can just, if there is a focal point, this white geodesic can be moved to purple geodesic without changing the length. Okay, at least first order. So this how to say? This white geodesic can move to the purple geodesic by just changing like this because of focal point. So at least the first order, it's okay. It's totally fine. It doesn't change the geodesic. But now this purple plus white has a kink, right? So therefore, you can just approximate like you can just smooth out like this way. Okay, you can smooth out like this. This has longer length than this purple plus white. Okay, so therefore, the purple plus white is the same length, has the same length as this white one. Okay, white one. So therefore, assumption will fail. So we assume that the P to this white one is a maximum length. But if you have a focal point, if you just shift this white to purple and smooth this kink, this yellow one has a longer length. Okay. Therefore, it's the assumption fell. So that's it leads to contradiction. So therefore, you cannot have a focal point P. So it's a proof by contradiction. Contradiction. Okay. Any question at this moment? No.
Can you repeat what was the contradiction there?
Okay, suppose the causal curve from P to sigma, which has a maximum length, okay, which has maximum length, has the caustic point in the middle, okay.
Okay.
Then this Q is a caustic point or focal point, and then this Q to sigma can be just how to say, just slide to purple without changing length, because that's that's the future of focal point as we found in the Euclidean part. So this is just like a changing red to blue is without changing the length from north to south pole, right? The geodesic stays geodesic by sliding. So that's the same thing. So that you can just slide this white one to purple one without changing the length. It's just still geodesic. But there's a kink here, Q. So purple to white, there's a kink here. But if you just smooth out this kink, this yellow one has a longer path, longer length. So therefore, this yellow one has a longer length than the white one. So therefore, assumption fell. So assumption is that this one, white one, is a maximum length. But if you have a focal point here, you can create the longer path by yellow. So therefore, the assumption fell. So that is a proof of contradiction. So you cannot have the focal point in the middle.
Well, in this case, when you smooth the way, the trajectory, the length will decrease, right?
Yeah, in the Euclidean case, but here it's an increase. Because I mean, it's like this example of the null case, right? If you just smooth out, if you have like a null one, but you can approximate by time like, right? This one has a longer length, right, in Minkowski's image, okay, than yellow one. So if you just smooth kink in Minkowski has a longer length. That's why. Okay, I was planning to go to some singularity theorem. Let's take a break, and I'm going to take after the break. I will talk about that. Using this one, I will show the singularity theorem by using this. Okay, let's take a break.
打字这种说的，这个咱们俩。又不是看你那个记得上，没手还有不是工作没有这个。是6张，不过2张这个后面2个是重复的。不是这个是重复的。这个看到也是重复的。可以填掉。
经过养补。 Okay, then shall we resume? Okay, I think in my lecture note this part is poor written. I didn't have a time to write down. So this kind of expression I didn't write down. So can anybody write down? Well, I have to write down later. But anyway, I will improve this part in the lecture note later. At this moment, I just explain by blackboard. Okay. Big Bang, Singularity Theorem. Okay. So let's write down statement. Okay. Globally hyperbolic. Hyperbolic. Space-time. M and G. And we consider sigma is Cauchy surface. And then what else? And the extrinsic curvature. So, okay, extrinsic curvature. With respect to the past directed time-like curve, time-like curve is negative. Is some negative. Okay, negative. C is some negative constant. This is just negative constant. Negative constant. Then, so this is a condition. This is a condition. And this is a, how to say? The conclusion, this is a conclusion, any time-like curve, cannot extend by proper time 3/c in the past. That's the statement. Okay, but most likely it's better to replace it because I just read too much. This is a condition, and the conclusion is any time-like curve cannot extend by proper time 3/c in the past. Okay, let's examine statement and then so on. Sorry. Okay, what is the extreme curvature K with respect to path directed? K mu nu, as I mentioned, K mu nu can be defined del T, H mu nu del T, del X mu. So this is the extreme curvature on the hypersurface, so sigma. And then H mu nu is the H mu nu. H mu nu is the, as I mentioned, so this is G mu nu plus Xi mu, okay? Xi is the orthonormal, Xi mu is the orthonormal, how to say? Orthonormal time-like vector, orthonormal to sigma. And this is the induced metric, and T is the proper ranks of Xi mu. Okay. However, so now the extreme curvature with respect to past directed time path curve means that you have to take the Xi in the opposite way. Okay. So if you consider this is the time direction, so therefore, if you use a yellow T, you have to simply put the minus sign here. Okay, it's simply you need to put the minus sign. So in Fulkerson theorem, so we use and as I mentioned, the contraction K mu nu, H mu nu will give you K, which is equal to theta in the Ricciardo equation. So in the Fulkerson theorem, I just assume that theta 0 is negative in the future directed. It depends on future directed one, but we can use the past directed one too. I mean, it just change the how to say, the time arrow in the opposite way. Okay, in the opposite way. Okay, so I use this future directed time-like curve for Xi. So this is Xi mu in the previous explanation, but now we just changed the time direction into the opposite way. So therefore Xi is now past-like. So the time direction can be understood as this direction is the time future direction. But now we can just consider the time direction is the opposite, and then the curve is just really focusing on past. It's totally free to do that. Okay. Why this is the so before giving a proof why this is called singularity theorem, so why this is the important? So the FL RW mentioned that in the past predicted in the past the universe shrinks to point. So that's a prediction of the FL RW. But here the homogeneous and isotropic is used. Okay. So at that time, so this feature, if you go to the past, that the universe shrinks to the point is due to this like a very ideal assumption that the universe is homogeneous isotropic. But Hawking mentioned that this is not the case. I mean, even you forget about the homogeneous isotropic condition. If it is just global hyperbolic, and the extreme curvature is in the past directed extreme curvature is negative, we have to inevitably see that you cannot see how to say time. You cannot extend a proper time longer than 3 over c. So you cannot extend the time like so that somehow proper time should end in the past before 3 over c. That's the statement. Which means that you cannot extend, which means that you have to inevitably see some singularity. Okay, let's give a proof of this theorem. So suppose by contradiction, so proof by contradiction. contradiction. Suppose there exist time-like path-directed time-like curve. Time-like curve. With length greater than 3/c. So there's this cosine surface sigma, and they exist the point P, and such that the time-like curve, the proper time is greater than 3/c. Okay. And suppose you can, you can maximize this the time-like curve from P to sigma. They maximize this time-like curve, then it becomes geodesic. But still, it's just if you maximize that, the still length is greater than 3/3. Okay. If you have a time-like curve, maybe time-like curve maybe something like this way, initially. But you can still like a longer, you can find always longer path from like this way by considering a geodesic, like this way. Okay. Then now, the previous assumption that since it's a space-time global hyperbolic, the longer path from P to sigma cannot have a focal point. Okay, but still, with focal point, cannot have a focal point. But still, the length is 3/c. The focusing theorem tells us that there must be, since the curvature, extreme curvature K can be identified with theta. Okay, it's negative. There must be a focal point. Before 3/c. Before 3/c. That's the focusing theorem tells us by the Ricciardo equation. So therefore, it's a contradiction. There's no way to extend the time-like curve in the past by length 3/c. It's a very simple proof. Okay. So therefore, this means that from sigma, there's no way to extend the time-like curve by proper time by 3/c, which means that there's something. There's something you cannot extend the space-time in the past. So that's the case, and we don't use any assumption except the global hypervelocity in the space-time. Okay. And then this extrinsic curvature case. If it is positive, if K is positive, there must be a singularity in the future. Okay, in the future. But in our universe, that's not the case. So therefore, it's very simple. So this is a cosmic example, Big Bang, and then we also encounter the singularity in the space-time, which is called black hole. So that is Penrose. So, okay, before maybe if you go to before Penrose. So cannot extend means that they cannot extend extreme curvature, so they cannot extend it in the path. This means the space-time is geodesically incomplete. Okay, incomplete. So if you cannot extend, for instance, Euclidean example is something like okay, even R is okay. R2 more 0. This is also geodesic incomplete. So if you just R is some plane and consider the you get rid of you get rid of the in the origin, then geodesic something like this cannot extend from the origin, right? You cannot extend it. So this is called geodesic incomplete in R2. R2 mod 0. And so on. So there's something going on in the origin. The same thing happened in this example. You cannot, in the past, you cannot extend the space-time must to end in the past. So, and then trough surface. So Penrose, black hole, Penrose, black hole, black hole, singularity theorem, okay, Penrose. Okay, assumption. Okay. So assumption. Okay, maybe this is called. It's not condition. Assumption. Okay, assumption. This is assumption. Okay. M G. Again, the global hyperbolic, and again sigma is Cauchy surface, and then here new energy condition assumed with new energy condition. Okay, and then if M contains a trough surface, okay. If trough surface exists, if trough surface surface exists, then the ongoing, then the trough surface T, I call it T. Then no geodesic from T must end. Let's see how to say. Cannot extend. Oh, sorry. Extend the affine length longer than 2 over theta 0. So that's the statement. So I will explain what it means. So first of all, what is a trough surface? So what is a trough surface? So trapezoid surface is that the surface. Trapezoid surface is a surface of which. Let's see. So in the case of in the Schwarzschild, so let's consider example. Schwarzschild point here is that the null geodesic is okay. Let's consider around here, right here. Null geodesic is this is outgoing null geodesic. First of all, this point here is every point here is a sphere, S2, okay? Because we projected the point. And this is called outgoing null geodesic, outgoing. And this is ingoing. It's called ingoing. If you consider the space-time, so this point corresponds to the sphere, S2. And you can omit outgoing is that you can omit the light into the outside of the sphere. Like I think like this way. This is outgoing light or whatever. Outgoing light should be something like this one. I don't know, whatever. And this is outgoing light. Outgoing light. And this is the ingoing one. Ingoing one. Okay. Anyway. Okay, these are ingoing one in the light. And so this is the case. And as you can easily see from the intuitive flat space intuition that the outgoing one, this geodesic congruence is positive, right? It's just if you just go into the sphere, it looks like it becomes bigger, right? So if you just consider the like geodesic, the sphere looks like it becomes bigger, and the outgoing one. So ingoing one is smaller, it becomes smaller. So okay. So the congruence is negative for ingoing, but the congruence is positive in outgoing in the flat space-time intuition. On the other hand, if you look at the point here, okay, maybe anyway, yellow. Maybe I should use yellow. The point here. So outgoing one also hits a singularity, and ingoing one also hits a singularity. Okay? So which means the outgoing one also null geodesic congruence is negative. Even if you send the light to the outside of the sphere, eventually this null geodesic will just shrinks and it hits to the singularity. Okay, hits the singularity. Okay. In this case, this point is called trapezoid surface. Even if you omit the light on the outside of sphere, the new geodesic congruence is just converges and it hits to the singularity. Okay, inside the horizon. So that's the trapezoid surface.
In other words, every surface inside the even horizon is trapezoid.
Yes. In the case of Schwarzschild. But this is the assumption of the if such a surface exists. That's the assumption of the Penrose theorem. In fact, so this assumption is Penrose. Penrose is that's how Penrose how he got the Nobel Prize 65. But then Sean and Yao. They wrote two papers. One is the proof of positive energy theorem. The other is this singularity theorem. But here Sean and Yao show that a certain condition with the energy and so on, they predict they can show that the trapezoid surface exists. So no need this assumption. There's some other assumption you can use to show that there's a trapezoid surface. This one is 80 something. I don't remember. Showing 83. This is a bit better proof in that sense. Anyway, so this is a mean or trouble surface. What is theta 0? Theta 0 is the what was that? Theta at the trouble surface T is equal to new congruence is theta 0. So this is the no geodesic congruence at trouble surface T. Theta 0 is this. Okay. Anyway, so this is the explanation of the terminology. Okay. Now let's consider the following thing. So important part. Okay. From now on, I'm going to show the following. Cauchy surface, did I write the non-compact? The Cauchy surface, okay, I should write that. Okay. Non-compact Cauchy surface, non-compact. This is important. Cauchy surface. I will show the proof. First of all, we consider the boundary of J plus of T. Oh, okay. Again, proof by contradiction. Proof by contradiction. And then what we are going to do is to assume, suppose, geodesic from T can extend longer than 2 over theta 0. Okay. Then we will show. So this is strategy of we will show. Boundary of this, how to say, what is called, J plus a future of T is compact. So we will show that the boundary J plus is compact. But however, there is no compact achronal. So this is also achronal. Okay. Achronal. Hypersurface. Exists. There's no exist. M in global hyperbolic surface GM. So this is how we show the idea of proof, the strategy of proof. So first we assume that if there is a new geodesic from T and longer than the 2 over theta 0, we show that this boundary of this, what is it called? I don't remember the terminology. It's called future, what was it? J plus is what, how do you call it? J plus? Causal future of T. Causal future boundary causal future of T is in fact the compact achronal hypersurface. Hypersurface meaning codimension 1. Okay. But however, so we will show that from now, there does not exist. There does not exist a compact achronal hypersurface in image. That's the. So first, let's show first the last statement before going to the first step. Okay. The hypersurface, so it's a Cauchy surface. So it's M is this global hyperbolic space-time, and the sigma is Cauchy surface, non-compact, compact, Cauchy surface. Okay, Cauchy surface. So let's go non-compact one. Okay. Any point P in the future, any point P can causal curve can just intersect the sigma. So we know that's the definition of the Cauchy surface. Okay, and if the so therefore, if there's a hypersurface, okay, achronal hypersurface, it has to embed in sigma prime by just connecting the time-like causal curve from sigma. Okay, any achronal one, okay, can embed to sigma by just connecting this achronal. Let's say sigma prime. Can embed sigma by connecting the causal curve one-to-one correspondence. Okay. In this case, the sigma prime has to be embedding on non-compact curve hypersurface has to be non-compact. Okay. You cannot embed compact. So this is d-1 dimensional hypersurface. This is d-1. You cannot embed compact d-1 dimensional hypersurface to the non-compact d-1 dimensional surface. Let's give you an example. R is a non-compact one. S1 is the compact one-dimensional manifold. There's no way to embed S1 to R. Okay. If you try to squeeze S1 to R, you have to really squeeze into the like this way. Like this way. But this is not the embedding because there is some endpoint here. Okay, this is not embedding. So therefore, the embedding for the same dimension has to be into non-compact one is that the pre-image has to be also non-compact. Okay. So
what is your definition of compactness here? Like it should be closer or something like
compact definition of compactness. I mean, I can give you a mathematical definition, but that's not the. Any covering has the finite many covering. That's the definition of compactness. But okay, maybe you can say. Compact means some closed manifold inside a bounded region. Some manifold in the bounded region. So that can be the definition at this moment. It's a bounded region.
just closed manifold.
I mean, for instance, open segment 0, 1. Here is also. So like an open segment is also bounded, but it's still open. It's non-compact. It's non-compact. But if you just consider endpoint 0, 1, if you include the endpoint, it becomes compact. So Yeah, I mean it's so therefore bounded and also it has to be closed. So this is not closed, right? It's open, right? So it's a bounded, but it has to be closed. So that's the definition of compact. Okay. For instance, you can have a compact hypersurface like this way. But that's not achronon, right? Achronon. So you can have. Okay. You can have this kind of like a time-like curve and that connect between these two. Okay. So that's not achronon. So therefore, in global hyperbolic with the global hyperbolic spacetime with non-compact causative surface sigma, there is no compact achronon. This is not achronon. Okay, there is no compact achronon hypersurface in spacetime. Okay, so that's the last statement. Okay, so now from now on, we just show that if you assume this one can create this boundary of J plus. Is in fact is compact and achronon. So therefore, this contradicts with the property of spacetime. And I can erase this one. Okay. Suppose so. Let's see. T is some how to say the tropical surface, and then you can just from here you can just extend it and how to say geodesic new geodesics. Okay, new geodesics. Something like so this length is the greater than 2 over theta z. Okay. So suppose there is such a new geodesic exists. Then we know that there is a focusing theorem. There exists a focal point Q before 2 over theta 0, which means that there is some new geodesic will converge up. It's still no. So it's still no, but somehow converge like this way. Okay, like this. Okay.
If it is no geodesic, the length should be 0, right?
But this is a fine parameter. I write down a fine length. A fine length. Okay. So the focusing theorem that the existence of focal is a caustic point. Okay. And then this caustic point here, it's hard to it's hard to draw. How should I write down? So, and if you look at the point here, the point here, so let's go P here. The same reason, it's a focal point. So therefore, you just okay, slide this how to say this new geodesic to orange one, then you can still find something. There's a kink, right? There's a kink, and so therefore yellow one, this smoother one, has a longer geodesic. This point and this point, yellow point with time-like curve, has a how to say longer length. Okay, do you understand what I mean? So therefore, this point is not inside a boundary of J plus. Do you understand what I mean? Boundary of J plus. So for instance, T. So I just write down D, T, and J plus is. I mean, if you intuitively, this is J plus of T. Intuitively, the boundary is always has to be null. Okay. It has to be always null. Boundary. So this is the boundary of J plus of future domain J plus of T. It has to be null. But in this case, point P can be connected by time-like curve. So therefore, it has to be inside. It has to be inside. So this point P is inside of J plus. Okay, J plus. So therefore, since there is a point Q here, and all the new vector is just focusing on Q. Okay, Q. So therefore, from here, one can just create, roughly speaking, J plus. Okay, maybe I should use the blue one. One can create a J plus like this way with T. So this is the boundary of J plus of T. Blue and bind J plus of T by null geodesic, by focusing point. So this becomes compact, and then a chronon. Okay. So this becomes everything a chronon. So this point everything is like, and so this point is compact a chronon. So that everything just is connected by null vector. So therefore, it has to be really boundary of this one. The boundary of this one. But so if you just go beyond this focusing point, focal point, then there must be some time-like curve that connect between these two by just again the just smoothing out kink. So therefore, if you can extend more than 2 over theta 0, so since there is a focal point which just converge all the new geodesics on the point, so you just only sweep out all the new geodesic from time t to the focal point, you can construct the compact achronal, the hypersurface. So which contradicts with the last statement we already saw above. So therefore, so you can prove that there does not exist such a you cannot extend the new geodesic with a fine length, longer than 2 over theta 0. So that's the idea of the proof of Theorem. I mean, this is a rough idea. I mean, if you want to see Walter's proof is not so good, but Witten's paper has a beautiful explanation. I mean, if you want, this is a sketch of proof. But if you want, you can just give you the more precise argument in Witten's paper. But anyway, so that's the idea of proof. So important part is that there's a focusing point. If you go beyond that, you can just connect again. There's the same thing. So if you just have the focusing point of null vector, and then if you just go beyond that, there must be some kink. You can create a kink, and you can smooth out kink by time-like curve, so that it has the it's no longer the boundary. It's no longer a boundary of this J plus. No longer boundary J plus, so that you can create some compact new hypersurface, which is achronal.
Why specifically 2 over theta 0?
Because focusing theorem tells us that the Le-Chatelard equation. So as we know, d theta d tau plus theta over 2 has to be less than 0 with the new energy condition. That's what what the Ricciardo equation tells us. So therefore, by focusing theorem, by using this one, theta inverse less than theta 0, so greater than, sorry, plus tau over 2, okay? Tau over 2. Is it the case? Inverse, sorry. Yeah. So, okay. So if you assume theta z is negative, in the future, like, there must be focal point or cosine point will exist with alpha line less than tau over 2. So therefore, Ricciardo equation is very important. This focusing theorem is very important to prove the singularity theorem. Any question at this moment? So that's the proof of the parallel singularity theorem. Yeah, I haven't write it down the precisely state proof of this one in the lecture note. Most likely I will try if I have time, but anyway. Anyway, so that's the parallel theorem. So parallel singularity theorem. Okay. So this is the so, and I just want to make a comment that the non-compact coefficient means that here a non-compact is important because I use the non-compactness to show this statement, the last statement here. So then this non-compact means the asymptotically flat. So the global space-time M is asymptotically flat. Totally flat. And then this okay. So therefore, so this would suppose that there is some singularity in space-time. Both Hawking and Penrose, there must be exist singularity. It's inevitable to have the singularity in space-time, and then people now have to accept the singularity in space-time. And there, so we need to understand that. That's why people just want to understand what is the quantum gravity and so on. What's going to happen when the physics del x is less than Planck length and so on. Well, what's going on? So these are natural questions one can ask, and nobody knows that yet. Okay, so that's the proof. And then from now on, my plan is going to ADM energy momentum charge. Any question at this moment? Okay. Then I just give you some definition of ADM energy, and then maybe short sheet case I can compute. Okay, so. Yeah, compact electron and no hypersurface. Okay, ADM energy. So we studied the Schwarzschild black hole and the curve and rational Nordstrom and so on, and the mass and angular momentum and charges up here. And the question is, how can we measure from a simple like a flat spacetime, the far region of a single flat spacetime? How can we measure this mass and charge and momentum, angular momentum? And that is the first calculation by this ADM. I'm very sorry, but ADM means the acronym of the person who derived. I know M is a Misner, but I forgot the A and D. Sorry about it. And so next time I will add the reference.
A is ordinal because D is the decimals.
Okay, thank you very much. Okay. Fine. So the simple flat space, we know that the everything is just dt square plus. So asymptotically, so okay. ds square is r goes to infinity. So that's what we already knew. We know that the in the what was that? Rational Nordstrom case, the charges will appear like 1 over r square. We know, and also angular momentum. So if you look at the the curve black hole, so angular momentum A part will appear like this way in the asymptotic like r goes to infinity region. So this is the rational Nordstrom case. The metric dependence is like this way for charges, and then curve case is the metric dependence appear like A over R cubed. So therefore, once you go to the really like R goes to infinity, dominant part is this side. Okay, dominant part is this one. Okay. So it's easy to capture M. In fact, so that's how the ADM first found how to measure energy from the infinity. And then so to measure the energy from infinity on some flat region, we just do the following decomposition of the metric. Eta mu nu plus h mu nu. Okay, and the h, so we assume this one is the order 1 over r, as we saw here. So we just forget about the charges and the angular momentum at this moment. Okay, and then write down the linearized Einstein equation. Einstein equation. So we know eta mu nu is just a flat metric. So the curvature can be written this h mu nu, and just write down Einstein equation. And then I'll be schematic. So Einstein equation is something like a quadratic in h. So roughly speaking, something like this way: h mu nu plus del mu h alpha, and then similar thing happen. Okay, let me write down everything like this. Minus alpha h alpha mu, and this is equal to minus 16 pi g. And t mu nu minus 1/2 eta mu nu and t like this. Anyway, so that's the linearized Einstein equation by using this h. And we can approximate the 0 is equal to, from this assumption, is equal to del T Hij equal to 0. H mu nu, so okay. Okay, so that's the assumption. We can just assume this one. This is valid because I mean H mu nu in the Schwarzschild case, it's of course the metric is independent of time here, and also here it's also you can assume the how to say zero I. Okay, I cannot justify 0. This one is almost like a perfect fluid case. Perfect fluid. Okay, let's assume this one. I cannot justify physically at this moment. So next time I will explain. Sorry about it. Then, so this one can reduce to the following calculation. Hij minus del I Hji Jj is equal to 16 pi g T00. T00. And we know that the so this is energy density, so therefore we can just integrate out at the so we can integrate out to get the energy. Energy is equal to d cube x T00, and this is equal to 1 over 16 pi g divided by d cube x del I del j Hij minus del I Hjj. Okay, and then we just need to do the integral by parts of this one. So by integral, yes. Okay, any question? So this is the sum r cube. Okay. R cube. So we just now consider the time directions here, and then whatever. X1, x2, x3 directions here, and then we just integrate out this spatial surface to define energy here. And then now we consider the phi infinity. Phi infinity at the S infinity, I call it, this is the radius r, goes to infinity case. And can be obtained by the integral by parts. And this is equal to 1 over 16 pi g. And then S infinity and dsi. And then del j Hij minus del I Hjj. Okay. So that's the energy.
Energy of what?
Space-time.
Energy of space-time?
Yes. Space-time.
Is it mean like a potential energy? Something like?
No, I mean energy of what? Oh, that's a good question. So if you have, okay. So here we assume asymptotic flat space. Okay, asymptotic flat space. Call it flat space. Flat space. And we just consider r goes to infinity. So r goes to infinity. So the r goes to infinity. And then so this energy is the energy what's filled out inside. inside. So total energy inside this space is the can be computed by like this way, by from metric. So metric knows that's natural, right? So if you have an energy, that will affect the space-time curvature. And then...
This is something like potential energy.
What do you mean potential energy?
There is curve, right, near to the black hole. So if a particle approaches to the black hole, increases its energy, like how it increases? Because it decreases its potential energy.
Yeah, potential energy. Yes. So what else do you have except potential energy? You mean kinetic energy and so on?
Yes.
It's not kinetic energy. It's a potential. I wouldn't say potential energy. I mean energy inside a entire space. That's what I would say. I don't know. I mean if you write down structure metric, 1 minus 2m over r. dt square, whatever, plus this inverse dr square and so on. Is this m is a potential energy? Is it the right question?
It is mass.
Mass is equal to energy, right? But is it potential energy?
This is the cause of potential energy.
Cause
Minus.
of potential. Anyway, so it's the same quantity as I am here. It wants to measure. Okay. So here the derivative is the really we just use the orthonormal. So this is orthonormal xi and then xj 1, 2, 3. So therefore if you want to use arbitrary coordinate, we just change this derivative by just covariant one. So this is the orthonormal coordinate. But for arbitrary coordinate, we just change to the dsi, di, dj, hij, minus di, hjj, like this way. You need to change like this way. And I'm planning to give you the example of Schwarzschild. Schwarzschild case. So in something called isotropic coordinate, so Schwarzschild coordinate can be written like this way. I mean this. This is in fact the homework of next week or week after, something like that. So we can write down Schwarzschild metric like this way. GM. I just restore G actually. The other J, dxi, dxj. So this is called isotropic coordinate, where rho is equal to x squared, like this, or maybe just like this. Okay, and then in this case, hij is the minus 2gm over rho delta ij. Okay, so hij is the am I writing correct thing? Something strange. I think I missed something. It should be -4. It should be -4. Then it's consistent, right? I hope I'm not mistaken. Then, if you just write down like this way, so the Hij is like this way. I'll check this one. So this part I will really rush. So then the energy is equal to 1/16 pi g. Okay, and it's a 2gm. What was that? Let's see. So so you just plug this one into here. What would you get? What would you get? You should get the 4 pi r rho squared, which is the S2 surface. So this S infinity, the area S infinity, and the xi rho double 2.2gm, and the rho cube xi and rho, which will give you m. I don't know how to get this one. Sorry. How do you get this one? You just apply derivative Hij del j. What would you get? I think this is just a unit vector. Okay, I think it's just a normal calculation. So ds is something like a dsi is the this normal vector, this guy, and if you apply this derivative of how to say del I here, you get this guy, and if you just do the calculation, you get the m. That's, I think, how it works.
There's sum over I.
Huh? Sum over I, yeah, of course.
My I should be 7.
I runs for, okay, of course, sum over I. Sum over I is equal to 1, 2, 3. And then rho is the square root x1 square plus x2 square, x cubed square. Okay, so time is up. So then next time I will explain more detail about this calculation and then resume. Okay. And then, yeah, next time I will briefly explain ADM. So I'm not going to go into the positive energy theorem. Most of the next time, later part of next time, I will go into the black hole thermodynamics.